Okay, so for problem number 5, we're trying to prove these statements here about theorem 2.3.2. So we're dealing with an index collection of sets, which is denoted here by the subscript A, and each set, so this is each set belonging to this family, where the index comes from the set delta, right? So for item A, what we're trying to show is that the intersection of all the sets in the family is a subset of every single set. So we're saying A sub beta for every beta belonging to delta. So for every index in here, the intersection is a subset of it. So what we're going to say here is we're going to say let X belong to the intersection. So, and we want to show that that X is also in every set, right? So we're going to say, and let beta belong to delta. So we're saying that beta is within that indexing set, right? Note that as X belongs to the intersection of A, then by definition, then X belongs to A for every. So for every A belonging to the set of indexes, right? So as beta belongs to the set of the indexes, it means therefore then X belongs to A sub beta. So what we said here, hey, if it belongs to the intersection, then for every index, X is in the set that has that index, right? And as beta belongs to the set of indexes, then X belongs to A sub beta. So therefore, we have shown that the intersection is a subset of for every beta belonging to delta, because we took some element that was here and then we showed that that element must have been there as well. So that's it for item A. Now let's do item B. So we're trying to, the idea here is kind of the same, but now we're taking an element that is in every single set within that family and then showing that it belongs to the union, right? So what we're going to say is, let me rewrite this. We're going to say for B, let X belong to A sub beta. So note that beta belongs to delta, right? Because we have here beta belongs to delta. So what this means, so there exists some alpha belonging to delta such that X belongs to A sub alpha. And I'll just put a parenthesis. This is not necessary for the proof, but just so that you guys understand, in this case, so basically saying, hey, if X belongs to A sub beta, it means that beta belongs to the set of indexes. So then there exists some index such that X belongs to A of that index. And so what this means here is by definition, then X belongs to the union of A belongs to delta of A. So we just, the reason that we said this, right, may have seemed a little bit weird that we chose to say, okay, then there exists some alpha belonging to delta, given that we said, B belongs to delta. However, we said this alpha precisely because this is the definition for this union here. And so once we've said this, we can then say, therefore, is a subset of the union. Right, we took some element that was in A sub beta, and then we showed that it belonged to the union. So that's it for item B. And lastly, we want to do give a direct proof of part D that does not use part C. So let's go ahead and do that. And this is one called De Morgan's laws, which is about the complement. And so because this is an equality, we're going to use a chain of if and only if statements, because we do have to use a biconditional whenever we're doing equality, or use a two-part proof. But using if and only if statements is just shorter. So we're going to say we have that. So for item D, we have that x belongs to, we're going to first let x belong to here, and then show that x must also be in here. So we have that x belongs to the complement of the union, right? So we're going to say, hey, x belongs to the complement of the union. If and only if x belongs to the complement of the union, it means that x does not belong to the union, right? That's the definition of the complement. And if x does not belong to the union, because remember that for it to belong to the union, it has to belong to just one of the elements in the family. So if and only if, for all the sets within that family, x does not belong to it, right? If and only if, for all A belonging to the index, so for all items in the indexing set, x does not belong to the set, right? Because x can't be in any of the sets if it does not belong to the union. And if it's not in any of the sets, it means that if and only if, it actually belongs to the complement of every single set, right? So if for all x belongs to the complement, and so if x belongs to the complement of every single set in that family, then by definition x belongs to the intersection of all the complements. So if and only if x belongs to the intersection of every single complement, right? So our conclusion, therefore, is going to be, therefore, these are the same. Therefore, the intersection is equal to the union. Equal to the, complement of the union. So just to discuss this once more briefly, we began saying, hey, x was in the complement of the union, and then we reasoned all the way down to x is in the intersection of every single complement, right? But we could also, because we used if and only if statements, we could also have began here, and then we kind of reason up like so, and then we arrive there. So because we used if and only if statements, we're allowed to go in either direction, right? And so that is it for problem number 5.